dripping and this jetting. You can make emulsions very easily. But then Andy Utada came along. We called him Handy Andy. We called him Handy Andy because he went to France to show some friends of mine in France how to make these devices. And in France, they don't say Andy, they say Andy. And Andy, yeah, Handy. Well, he is handy. He was very handy. And he was another graduate student. And like all good graduate students, all really good graduate students, he made mistakes. But he learned from his mistakes. So Andy, he connected things in the wrong way. But it was a really brilliant solution to a problem that we didn't know existed yet. So he, instead of doing it the normal way, instead of doing it in this co-flow direction, everything in the same way, he connected it backwards. So now the outer fluid came this way, and the inner fluid, instead of coming in this direction, came in the opposite direction, but he collected everything through the same orifice. That works just as well, but now the outer fluid is flow focusing. You're getting hydrodynamic flow focusing of the inner fluid. So you're making even a thinner stream through here. And that works really well. Here's the dripping case. You can see the drops being formed. And you can form a jet. You can't even see the capillary, the collection capillary, except for this piece of dust because the index of refraction is the same as the oil. In this case, now remember, this fluid is coming from over here. And this other fluid, the outer fluid's looping around from this side. But it works just as well. But what's really interesting is, look, here's the same thing, a slightly different geometry, the same thing, where you're doing this flow focusing. But look, remember we said we can align things very easily. So we can align a second capillary tube now. And now we can have a co-flow here. So we have a coaxial fluid and a flow focusing here. The flow focusing is not focusing one fluid, but it's focusing a co-flow, a coaxial co-flow of two fluids. So again, it's very easy to make this. One, take a second, align that. It really, you can align it very well. Now you can see in the microscope, you can align this very, very simply. You can make this in a very, very simple way. And this is what it looks like. This is the way it works. Here's the two fluids. You can see they're collecting. Maybe it's easier if I show you this image where I'm showing you the same device just changing the flow rates. And look what you have. You have a co-flow, so you have one drop inside of a second drop, one drop inside of a second drop. Varying the flow rates, you vary the relative size. You vary the size of the core and the shell. Here the shell is really thick. Here it's getting thinner. Here you almost say there's just a single drop, but it's not. There's really a shell. Look, one fluid here, a second fluid, and a third fluid. And if you look very carefully, you'll see that there's a thin shell. So just by adjusting the flow rates, now you can make something much more complicated. You can make a double emulsion, a core shell structure. Actually, this is something that's commonly made, but the way you normally make a double emulsion is you make one emulsion, shake it up, and you take that and put it in the second solvent and shake it up. If you're doing this, the polydispersity that you had in the first place is squared. You get twice as much. You get the square of the polydispersity. And here, just to show it, we put the innermost fluid, we put a dye in it, and you can see sometimes you get this nice core shell structure, sometimes, but often you get many drops in the inside, no drops in the side, some funny drops. You get all wide distribution. Whereas in this case, you get a perfectly uniform core shell structure. This is already something that's very, very interesting. Let me show you one simple but very important application. Imagine that I make a structure where the innermost fluid is water, and the outermost fluid is also water, and the shell I make out of a solvent. And in that solvent, I put some kind of surface active molecule, a surfactant, a phospholipid, a diblock copolymer, something that likes the interface. Then it will coat this interface and it will coat this interface. So both the interfaces will be coated by these surface active molecules, surfactants, phospholipids, diblock copolymers. If then I make this solvent volatile, I can evaporate it. And then what am I left with? I'm left with the bilayer structure of surfactant, a phospholipid, of diblock copolymer. If it's phospholipid, what's that called? A bilayer structure of phospholipid is called a liposome or a vesicle. Liposomes or vesicles are often used for encapsulation, particularly of drugs, because they look sort of like a cell, so they're nice to encapsulate. But to do that, the normal way of doing that is you take these phospholipids, you make a multi-layer structure of these things, you put the drug in water, you bubble nitrogen, and they self-assemble into these bags that contain everything. That's good. That encapsulates things very well, but this very valuable drug that you're trying to encapsulate is everywhere. So you've just encapsulated a small fraction of it. Here, the drug can be here, and this fluid and this fluid are completely different streams. So now you can make really nice encapsulation structures very, very simply. Actually, it's sort of interesting. Here's an example. Here we've encapsulated a dye using, in this case, diblock copolymer. So these are polymerosomes. We have a little extra polymer here because you always want to have enough to make sure that you completely cover the surfaces. So you add a little excess. You can see this little ball. This is encapsulating a dye. And I can come back months later and the dye is still always encapsulated. It's perfectly encapsulated. It's actually interesting to watch what happens. This is what happens as the solvent evaporates. This is just a series of images. See what's happening? Let's see. I show it here. This is the bilayer structure, and this is the solvent evaporating. This will eventually evaporate. But notice there's a contact angle. There's a well-defined angle here. The fact that there's a contact angle means there must be adhesion between the two layers. So we know right away that this is a slightly adhesive structure. If it's slightly adhesive, that's actually a somewhat solid structure. Can I prove that to you? Well, I can prove it to you by trying to crush the structure. So how can I take a structure like this and crush it? Well, I could take a hammer. I could take a pressure. The trouble is that doesn't work so well in water. And putting a hydrostatic pressure, just putting high pressure on, go to down, deep hole in the ground or put under pressure, that doesn't really do it. What I need is an osmotic pressure. I need something that puts a pressure on the water on the inside. And I can do that just by putting something on the outside that will suck water out. So I put something that will try to collapse it, will try to crush the structure. And if I do that, it looks like this. You see it's being crushed, but look how it's being crushed. This is round, and it's crushed here. It's buckling. It's the same thing if you take a piece of paper and you put a compression on it, it buckles. And something that buckles must be solid. So you know that this is a slightly elastic shell that's buckling. And I think, in fact, I show you here by measuring the number, the fraction of the shells that are buckled as a function of the pressure, you can actually calculate the elastic energy of the shell. And in fact, one thing that's interesting, look at the pressures that you need to break these things. These are measured in atmospheres, 5 and 10, 15 atmospheres. That's a fairly large pressure, but from an osmotic pressure, it's not that large. So I showed you can crush it, but actually, it's sort of interesting. Let me just crush this with an osmotic pressure. So here's I'm crushing it. It gets smaller and smaller, and eventually, I crush it down to nothing. Now imagine if you're something that's on the inside. Unless it's a very, very large molecule, it's been crushed and it's been squeezed out. So what have I just showed you? I've showed you not only how to crush it, not only how to encapsulate something, but also how to release it. I squeeze it out by putting a pressure on it. Actually, there's another way of doing that, and that is not to crush it, but to explode it, to put it in a very low osmotic pressure and use the pressure of whatever's on the inside to break it. So here we've taken those same dye-containing polymerosomes and we've put them in pure water, and you can see that a little hole has developed here, and I would show you a fluorescence image of this, but the dye has escaped. All of the dye is gone. Actually, it's interesting to watch. This is one of these polymerosomes, and this is now put in a low osmotic pressure to watch it explode. And look what happens. You see how it gets larger? Water's rushing in, and then boom, a little hole develops and it starts to shrink. Watch this one. Gets larger. It always gets larger because water rushes in. It's got this low pressure on the inside. Water's rushing in, and then it completely disappears. So here's a second way to break the, to release it. You can do all kinds of things. I won't show you anywhere near the number of things that we can do. You don't have to, for example, evaporate the solvent. You could polymerize the solvent. This is the same shell, but we use a UV curable resin. These are polymerized. These are thin shells. You know that because the only way you can crush them is to put them between two glass slides and just squeeze really hard. And you can crush them. It looks like this. And you can make a wealth of different structures.